let's talk about options. My name is Brendan Burns, and my project is called Jade Lizard. This is what my project looks like, and to give you guys an introduction before I start talking about the details and the code itself, my idea for my project was to create an interactive web application in which users can interactively build and then graph the profit and loss for option strategies with all the data being entered by the user. And before I start talking about the architecture of my project and how I do that, I'm just going to quickly go over some basics about options so you understand why I did this and just some technical background about options. So for those of you who don't know, this is what an option listing on an option chain looks like. So you're buying 100 options for Apple stock with the expiration date at June 17th, 2016, with the strike price at $105. And just to break down what all of this means, when you're looking at an option, the important terminology is the underlying instrument, which is usually the stock, but it could be a future or an index or a commodity or pretty much anything that the option that underlies the option. So you're tracking, and the option will relate to the price of that underlying instrument. And then you have the position of the option, whether it's long or short, which is the same as whether you're buying or selling the option. If you're selling the option, you're receiving a premium. It's also known as writing an option. And if you are buying an option, you are paying someone else a premium for that option. You have the type, which is either a call or a put. Buying a call option gives you the right to buy a stock at the expiration date or before if it hits the strike price. And buying a put gives you the right to put or sell the stock at the strike price. The expiration date is the last date at which you can exercise your option. So after that, either you cash in or your options expire and they're worthless, which kind of makes options it's one of the things that gives them their risky nature, because after expiration, either you've made money or, with a naked option, either you've made money or you've lost it all. And then the strike price is the price of the underlying stock at which you can exercise your option. So with this option here, if Apple stock hit $105 for this call, you then have the right to buy Apple at that price. And then if it goes above or below, I'll show you what happens to the profit, but that's the main terminology. And then of course you have the premium, which is the value of the option. You can look up the real-time prices online, or what I did is I used pricing models to calculate theoretical value. More about that later. A little bit about how option profit and loss works. With the option I showed in the previous slide, if you assume that the price of that option is about $3.50, and you usually buy options in tranches of 100. So let's just say the cost of that strategy is $350. If Apple stock goes, it's about $92 right now. If you buy that option and before June 17th, it goes up to $112, which is not that big of an increase in the price of the stock, you can make 100% profit on those options because of the way they're structured. But if the option doesn't hit the strike price, you actually lose all your money. And it'd be the same in reverse if you made it a put and the stock moved in the other direction, but just so you understand how options work and how they track the underlying value. So my application revolves around interactively building option strategies, which are a way of creating basically groups of puts and calls that you can customize for any movement in the underlying stock. So in the example I just showed you, if you wanted to maximize your profit in this scenario, you want Apple stock to go as high as possible. But if it doesn't hit the strike price, you lose all your money. But maybe you want to create an option strategy in which the stock does absolutely nothing and you still want to make money. And there are ways to do that with options. So right here on the bottom part of the slide is a little screenshot from part of my application in which I've built this option strategy where you sell a call and a put around the price of the underlying stock, and then you buy a call and a put at a spread about $10 away from the underlying price. And to give you an idea, if you were to graph this, and I did that with my application, you get this. This strategy is called an iron butterfly. And it's just an example of how you can use an option strategy to make money. In this case, your profit is maximized when the underlying stock does nothing. So if it's at $100 and then your options expire and the stock is still at $100, that's when you maximize your profit. So what I wanted to do is give users the ability to build any strategy they want interactively and then graph it and see what would happen. And these are just a couple more examples of how you can build a strategy to maximize profit no matter where the underlying stock is. When looking at the tools that are available online for people to work with options, I noticed a few things. I made a list of just different web applications that you can find. There are lots of different solutions for pricing options with different models, which I'll talk more about later, or tools for researching option chains, so quotes for option prices, or if you want to, there's actually even programs where you can say, I think the stock is going to be here, find me an option strategy. You can even do that. You can calculate Greek values for options, which I'll talk more about later as well. They're measures of, they're basically derivatives that calculate what will happen to an option price based on certain changes in the market. But what I'm saying is there are lots of different tools available online, and there are actually a few pricing libraries, both for Python and for C++, but I couldn't find a way for someone, especially who's not as well initiated into how options work, to just go and play around with them and create something, and in an interactive visual way to see how option strategies work. And so that was my goal, is to create a sandbox for visualizing and configuring and playing around with option strategies. Here's a map of the architecture I used. The user enters information for the option strategy through a form, which is then I use Ajax to send it to Django, which passes it along to my option models. And the option models take each option that the user enters and builds a strategy. And then for the strategy, it prices the value of that strategy for hundreds of different values for the underlying price with one of two pricing models. And there are multiple different ways to price options, and I'll talk more about that in a couple slides. But so the option models build a strategy, and then I price it with one of two models and send that back. And then once I have the pricing data, I graph it using D3.js, and I actually used C3.js, which is a charting library built on top of D3, which made my job a lot easier because D3 has a pretty steep learning curve. I'll just do this is a really oversimplified version of how my program works from start to finish. So the user enters all the strategy information. You can enter up to 6 legs. I limited the user at 6 for 2 reasons. One being that most option strategies are typically anywhere from 2 to 4 legs, so it's a reasonable range. But more importantly, if you're trying to calculate hundreds of prices, each time you calculate a price with a complicated pricing model, and then for more legs, it starts to get really CPU intensive, and I wanted to put some kind of limit so that the program wouldn't really slow down. So I capped it at 6. And then, as I said, the option models will build a strategy, and just like neighborhood GPS, I used the pandas data frame architecture to calculate the value of a strategy. So you enter your strategy information, it takes the underlying price of the stock to determine a scale. So if you say the underlying value of the stock is $100, it'll calculate prices every 50 cents to get a reasonable number of prices, and then it'll build a pandas data frame. And then once that's done, it takes that data frame, exports it to a JSON format, and sends it to be graphed. And that's pretty much it. A couple other features I added is the ability to calculate Greek values for both pricing models. And Greek values actually one of the biggest sources of pain during the development process because they involve a lot of different calculations, and because I built my project using floats, which I plan on changing in the future, you get a lot of tracking error when computing these values. But what they are measures of, they're derivatives that measure what will happen to the value of your option if certain things change. So delta measures the rate of change of your option price with respect to a change in the underlying price of the stock. Or vega measures the rate of change in your option price with respect to a change in volatility. So you know, well, I own this option strategy, but if the underlying stock is all of a sudden more volatile, what are the value of my options now? And then I added a couple features that let the user set the exercise type, American or European. So with the European exercise type, the modeling assumes that you can only exercise the options at the expiration date, whereas with the American exercise type, which represents the majority of options that people actually trade in the real world, you can exercise the option at any point before the expiration date if the underlying hits the strike price. All right, now I'm going to talk a little bit about the 2 pricing models I used. You can see the code in the background. The Black-Scholes model is the most commonly used model for pricing options theoretically. It's been around since the 70s, but it's actually still surprisingly accurate. and it's also the easier of the two models I use to implement. The limitations of the Black-Scholes model are, number one, that it is only representative of options with the European exercise type, because it finds the value of an option at a static point in time, and it makes a bunch of assumptions that are not necessarily true, which I won't go into. But the inputs are S sub 0, which is the underlying price of the stock, K is the strike price, T is the time to expiration, Q is the continuously compounded dividend yield of the underlying stock, R is the current risk-free rate of return, which is just the treasury bill rate, and sigma is the volatility annualized of the underlying stock. And obviously you can't be exactly sure what the volatility is going forward, but you can put in a proxy value. Basically, the way the Black-Scholes model work is you take two derivatives, which are D1 and D2 at the top, and you use those derivatives to calculate the price, and then all the rest of this stuff is just the Greek values, which are, as you can see, they're kind of computationally a mess. But second model is the binomial tree model, which you can use to price options with an American exercise type, and this is different because it builds a big binomial tree which models the option price at different points in time. So if you want to know what the price of the option is before expiration, you would use this model. And that's basically it as far as the architecture. So now I'll do a demo, after which you can ask questions. Anyway, here it is. I haven't deployed it yet, so I'm just running it locally. If you're wondering why I named it Jade Lizard, it's a type of option strategy. I thought it was a cool name. Probably makes no sense, but anyway. Here, let me blow this up a little bit. Alright, so we're going to create a strategy here. So we set the values that are constant for every option in the strategy. So these are values for the underlying stock. So we say our stock's at $100. Volatility we say is at 25%. Dividend yield maybe 3%. And then the risk-free rate, it's currently about that. It's pretty low. And then we add we add up to 6 legs. So those are the values we just entered up here. And so we'll add, let's just say we're going to short a call at 100 with 1-year expiration, and then we're going to, and you see it's showing up down here as I add it, and then we'll short a call at 100, and then we'll put a long call in at 110, and I'm doing all these with the same expiration date, and then we'll put a long put in at 90. And you can delete them down here if you want to remove them, but once you're done adding all the legs that you want, you hit save, and you hit graph. If you want to go back, go here and delete whichever ones you don't want. You hit save, you hit graph. And with C3 you can hover and use the tooltip to see the values of each point. You can select points on the graph and deselect them. And if you want to see a more specific range of prices, because this is going everywhere from 25% value of the underlying stock to 200%, you can use the range finder and see less of it. And I added a couple tools where if you want to get a more realistic value for volatility, so you're trying to like model this after a real stock, you could enter a ticker and enter any number of trailing days. So if you want to know what the annualized volatility of Apple was over the past year, you can put that in and you get 27.3%. And if you, for some reason, just want to know what the current risk-free rate is, you can just click here. And then, as I said, this is where you set the pricing model. So for Black-Scholes, you don't really have that many options because it's pretty standard. With the binomial tree, you can set the exercise type and the number of steps, which is basically the number of times the number of how big the tree is. And the more steps, the more accurate the pricing will be, but it's also much slower. And you can save that, and for this you won't see a difference in the graph. I don't know if you just saw that it changed very slightly, but when you start to have strategies with higher dividend yields or options that are further out of the money or calendar spreads, you'll notice a much bigger change in the graph. So that's basically it.